Okay, welcome dear students. Welcome to yet another video on electromagnetic field theory. So this video is about Smith charts. So if you have ever encountered Smith charts in such a way that you are not able to understand the MCQs which are based on the simple electromagnetic theory. There are so many complex circles in a Smith chart which makes this chart so jumbled up that it is very hard to comprehend what these circles actually mean. There are circles such as constant resistance circles, constant reactance circles, constant VSWR circles, constant reflection coefficient circles. Okay, and there are various scales which are also given in a Smith chart, which usually is not known to a lot of students. The MCQs which usually come in a GATE exam are not so complex, but if a Smith chart question is made tough, then these concepts comes very handy. Okay, so in this lecture I am going to give you a detailed study of Smith charts, its various scales, various types of circles such as resistance circles, reactance circles, etc. So at the end we have also solved few simple MCQ questions which are based on Smith chart. There are also complex questions which can be solved. I will deal with those complex questions in another video, because this video is already going to be very long, because I am going to first explain the different concepts, and then I am going to solve 3 MCQs based on this concept. Okay, so without wasting any time, let's start this tutorial.
Welcome dear students. This is a lecture on Smith chart. In this lecture we are going to study some of the basic points on Smith chart, which is important to solve MCQ questions which usually comes in a GATE exam. In this lecture we are going to see what is Smith chart, what are the types of Smith chart, measurement scales of Smith chart. So most of the engineers who study electromagnetic theory or transmission line theory do not know fully about the measurement scales of Smith chart. Okay, so this is an important topic. Next is constant resistance circle and constant reactance circle. A lot of questions has been asked based on this concept. Next will be constant VSWR circle and constant reflection coefficient circle. This is also an important concept when it comes to Smith chart basics. And then we will solve few MCQs based on Smith chart. Okay, so let us first try to understand what is a Smith chart. So a simple definition of a Smith chart is that it is a graphical tool. It is a graphical tool which is used to measure various transmission line parameters such as reflection coefficient, transmission coefficient, voltage standing wave ratio, load impedance, etc. Okay. So what are the types of Smith charts which are available? So the first type is impedance Smith chart. Next is admittance Smith chart, and the third one is immittance Smith chart. So the impedance Smith chart is used for series circuit. Admittance Smith chart is used for parallel circuits, and immittance Smith chart is used. It's actually a combination of both impedance and admittance Smith chart. Okay, all right. So before moving on to the measurement scales of Smith chart, I would like to first talk about the normalized value of the impedance. Okay, so let me so what is normalized impedance Smith chart? Usually you will find in MCQs that they use this word normalized. Normalized means the load impedance is normalized with respect to the characteristic impedance of the transmission line. Okay, so let us say you have ZL, which is the load impedance, which is equals to RL plus JXL. Now if you divide this load impedance with the characteristic impedance of the transmission line, so you can divide it here also and here also. So what you will get is RL plus JXL. So these small case letters R and X, they represent normalized resistance and normalized reactance of load. Okay, so RL is what? RL is normalized load resistance and XL is normalized load reactance. Okay, so in a Smith chart we usually plot normalized impedances. Alright, so this is a very important thing that I wanted to tell you. Next, you can also see that normalized admittance Smith chart can also be plotted. So that will be YL divided by Y0, which is equals to GL divided by Y0 plus JBL divided by Y0, which can be written as GL plus JBL, where GL is normalized load conductance and BL is normalized load susceptance. Okay, alright, so now let's move on to our next topic. Okay, so the next topic is measurement scale of a Smith chart. So the complete Smith chart looks something like this. So this is a complete Smith chart. In this Smith chart there are different types of measurement scales. I will show you one by one. So the first measurement scale which you can see in a Smith chart is along this horizontal line. Okay, so if you can see, this has various numbers written on top of this horizontal line, such as 0.1, 0.2, 0.3, 0.4, 0.5, etc. Okay, and here it is written resistance component R over Z0 or conductance component G over Y0. We have already seen that R by Z0 is nothing but the normalized resistance. Similarly, G over Y0 is the normalized conductance. Okay, alright. Next, we will see these measurement scales. Let me zoom it further. It says inductive reactance component plus Jx over Z0 or capacitive susceptance plus JB over Y0. Okay, so this is inductive reactance component plus Jx over Z0. So plus Jx over Z0 is nothing but plus J small x, that is the normalized inductive reactance. Okay, and if you see here, there are values such as 0.1, 0.2, 0.3, 0.4, etc. All these values represent the normalized inductive reactance of a transmission line, of a load. Actually, it's a property of a inductive load. All right. Okay. So these values are written all the way around this circle. If you go around this circle, these values are written. Okay, here also it is written 0.7, 0.6. But since this value at the bottom half of the Smith chart this value is minus jx over z naught. So this is minus jx small x. Okay, so the bottom half of the Smith chart represents capacitive load. So this half of the Smith chart represents the capacitive load, and this half, upper half of the Smith chart represents inductive load. All right, okay. Now let us try to see about the next measurement scale which is given in the Smith chart. If you see carefully, there are 4 different measurement scales given here. This is one scale, this is another scale, this is one more scale, and this is the 4th scale. So there are 4 different measurement scales given in this Smith chart. Now let us see one by one what are these measurement scales. If you go to the extreme left of this Smith chart, this topmost measurement scale, these values, it says wavelength toward generator. Let me zoom it further. It says wavelengths toward generator, and there is an arrow given which is moving in the clockwise direction. Okay, so these values 0.04, 0.05, 0.06, these values you can find all along this circle. All along this circle you will find these values. They are different values. So these values represent what? They represent wavelength towards generator. So whenever you move towards the generator, the amount of distance that you move towards the generator in terms of wavelength is given by these values. Okay. Similarly, if you see the next set of measurement scale which says wavelength towards load. Okay, this says wavelength towards load. Let me zoom it. Wavelength toward load, and there is an arrow given which is along the counterclockwise direction. Okay, so these values are also in terms of wavelength. So whenever you move towards the load, the amount of distance traveled towards the load in terms of wavelength is given by this measurement scales. Okay, these measurement scales can also be found throughout the Smith chart, all around the Smith chart. All right, okay. Now let us see the next set of measurement scale which is given here. For that you will have to move towards the extreme right of the Smith chart. Here you will find it is written angle of reflection coefficient in degree. Angle of reflection coefficient in degrees. All right, so these values, the third set of measurement scale, 20, 30, 40, etc., these values represent angle of reflection coefficient in degrees. Similarly, angle of transmission coefficient in degrees is the 4th measurement scale which is given in the Smith chart, which are these values 10, 15, 20, etc. So all these values, these 4 types of measurement scale, this represents 4 different types of parameters of a transmission line, which are: first is wavelength towards the generator, second is wavelength towards the load, third is angle of reflection coefficient in degrees, and 4th one is angle of transmission coefficient in degrees. All right. Okay, now let us see what is written at the bottom of the Smith chart. If you see here, it says radially scaled parameters. So the word radially means this Smith chart, from the center of the Smith chart, if you move radially in this direction or in this direction, then you can calculate different types of parameters. Okay, so these parameters are what? Let us look at the extreme left of this scale. So if you see this line, on top of this line you will see various values such as infinity, 100, 40, 20, 10, etc. So the values which are written above this line, they are standing wave ratio in linear scale. Similarly, the values which are written below this line, such as infinity, 40, 30, 20, etc., they are also SWR, that is standing wave ratio, but in dB scale. Alright, now if you see this particular line, on top of this line you will find values such as 0, 1, 2, 3, 4, etc. These values represent return loss in dB. And the values below this line, which is 1, 0.9, 0.8, 0.7, etc., these are reflection coefficient in terms of power. So that is why P is written here. If you see carefully, P is written here. So the reflection coefficient in power is, in terms of power, is mod of reflection coefficient whole square. And if you see this particular line, these values such as 1, 0.9, 0.8, etc., they represent reflection coefficient E or I. So E or I means this is actually the voltage reflection coefficient and current reflection coefficient. Alright. Similarly, if you move towards the extreme right of this scaled measurement scale, you will find parameters such as attenuation in dB, standing wave loss coefficient, reflection loss in dB, standing wave peak, and transmission coefficient in terms of power, and transmission coefficient for voltage and current. Okay, so now you have understood that a Smith chart offers various types of measurement scale with the help of which we can find out different parameters of a transmission line. Okay, now we are good to go. Next topic of the Smith chart, which is the constant resistance circle and the constant reactance circles. Alright, let's move on to the next topic. Okay, so this topic is constant resistance circles and constant reactance circles. Now if you see this Smith chart, I have drawn various circles using different colors. If you see the red color circle, this represents constant resistance circle, whereas the green and yellow color circles represent constant reactance circles. Now one thing that should come to your mind is that the green and yellow color circles are not fully drawn. That is because the Smith chart can only accommodate some part of the reactance circles. The remaining part of the reactance circle, such as if you draw the remaining part of the reactance circle for this particular graph, you will find that the remaining part of the circle is outside the Smith chart. Okay, so the normalized impedance Smith chart does not show the full circle of the reactance. It only shows a part of the reactance circle, which are shown here in green line as well as in yellow color line. Alright, okay. Now let us zoom in and see what these circles actually has to say. Now if you zoom in, you will find that, let me choose a different color so that you are not confused. Okay, so this particular circle, this circle, sorry, let me draw it once again so that you can clearly see. This circle which I am drawing right now is called a unity resistance circle. Why is it called a unity resistance circle? Because this circle passes through the point which says 1.0. Okay, so the value of this circle is RL is equals to 1. And if you notice, all these circles, all these red circles pass through this same point. This is the same point through which all of these circles pass. Not only just the resistance circles, but the reactance circles also pass through this common point in a Smith chart. And this point in a Smith chart is a very special point. Similarly, this particular point in the Smith chart is also a special point. Similarly, this point on the Smith chart is also a special point. We will talk about these points in great detail now. Okay, so now if you see carefully, the value of the resistance circle, if you move towards this direction, let me choose this color. If you move towards this direction, the value of resistance increases. So smaller the circle, the resistance value is higher. So let us take, for example, this circle has a resistance value of RL is equals to 2 because it passes through the point 2.0. Let me delete this so that you can see it. Yeah, so this is a circle which passes through the point 2.0. And if you see this circle, it passes through the point 5.0. So the value of RL here is 5. Okay, but if you move in this direction, you will see the resistance value is decreasing. So the larger the circle, the resistance value is smaller. So let us say for this particular circle, the resistance value is close to 0.52 RL. Similarly, if you take this outermost circle has a value of RL is equals to 0. So this is an important thing. Let me write this in the outer side so that it can be referred later. This is RL is equals to 0 point. Not only the point, the entire circle, the outermost circle, the biggest circle in the Smith chart represents RL is equals to 0. Okay, alright. So one may easily say that if the radius of these constant resistance circles decreases to 0, that means the circle no more remains and it just becomes a point, such as this point. Let me remove this particular point, this point. Okay, so if what I am trying to say is that if the radius of this constant resistance circle decreases such that the radius becomes 0 and it just becomes a point, then the value of the resistance is infinity. Okay, so this means that a circle with 0 radius will have a resistance value equal to infinity. RL is infinity. Okay, alright. Now let us talk about the reactance circles. So first let me choose the inductive reactance circles. So these green color curves, these are inductive reactance curves. Okay, because they are on the upper half of the Smith chart, so they represent inductive reactance. Okay, it is written in the Smith chart already. It represents inductive reactance component. Now if you see here, smaller the radius of the circle, the larger is the value of the reactance. So if you compare this value and this value, this is a larger value, 2.0. Let me zoom in. This is 2.0 and this is 1. And if you see carefully, that this circle has a smaller radius as compared to this circle. Okay, all right. So This means that smaller the radius of the circle, larger will be the value of the reactance, which means if the radius of the reactance circle is 0, then the value of the reactance will be infinity. That simply means that when we reach at this point, it also represents XL is equals to infinity. Alright, similarly, when the radius of the circle keeps on increasing and the radius of the circle becomes infinity, then we reach at this particular point, and this point can also be written as XL is equals to 0. So when RL and XL both are 0, we can say that ZL is equals to 0. That means this is a short circuit condition. So that is why I was saying that this is a very special point. So this point is a short circuit point. Similarly, this point is a open circuit point. This is a open circuit point, this one. Why? Because RL and XL both are infinity. RL and XL both are infinity. That is why we can say that ZL is infinity over here. So it is a open circuit condition. Okay. Now let us look at these yellow color circles. So these yellow color circles, these are capacitive reactance circles. Similarly, as in the case of inductive reactance, these circles also show same behavior. The smaller the radius of the circle, the larger the value of the reactance. So this, if you see here, this particular value is 2.0 and this is 1.0. So if you see, this circle can be written as XL is equals to minus J2. Okay, and this circle is the locus of XL is equals to minus J1, and this one is the locus of XL is equals to minus J0.5. Why 0.5? Because it is passing through the 0 point value. Similarly, in case of inductance also, this particular circle is the locus of XL is equals to plus J2, and this is the locus of XL is equals to plus J1, and this is the locus of XL is equals to plus J0.5. Okay, why 0.5? Because it is passing through 0.5 value. Alright, okay. Now before moving on to the next set, I would like to declare few things in this Smith chart. First is that this middle point in the Smith chart, this middle point in the Smith chart, let me choose a different color. Yeah, this middle point in the Smith chart is called a matched load point. Matched load. Okay, and this point we have already seen, it is called short circuit load. That means the load is short circuit. And this particular point we have already seen, this particular point, it is called open circuit load. That means the load is open circuited. Alright, and this largest circle in the Smith chart, that is this particular circle, the largest circle which is drawn in the Smith chart is this circle. This constant resistance circle is also known as purely imaginary or purely reactive circle. Purely reactive circle. Why purely reactive? Because the value of resistance is 0 in this circle. If you see, the value of resistance was 0 here. the value of resistance, slowly it became 0 when we moved towards the left side in this direction. The value of resistance was initially 1 at the center, and when we moved towards the left side, the value of resistance became 0 at this point. So this is a circle of zero resistance. So that is why we call it a purely reactive circle. Similarly, this horizontal line, this black color line, this is called purely, let me write it, purely resistive line. Okay, yeah. Why purely resistive line? Because this is the locus of XL is equals to infinity. You remember that when the reactance circle was a point, it was XL is equals to infinity. But when we increase the radius of the circle so much that the radius of the circle became infinite and it started looking like a straight line, which is this horizontal line in the Smith chart, we called it XL is equals to 0. So that is why this particular point is also called XL is equals to 0, and this is also called purely resistive line. That is also why if you see in this Smith chart, it represents resistance component. These values represent the resistance values. Okay, all right. Now if I talk about the last point in this circle, which is the point at plus J1, this is called purely inductive resistance, purely inductive reactance. So this is the point of purely inductive reactance. Okay, its value is plus J1. Similarly, the reactance circle which is passing through this one value, it is called purely capacitive reactance, and its value is minus J1. Okay, so this was all about the Smith chart, all about the constant resistance circles and constant reactance circles actually. Okay, in the next part we will talk about the constant VSWR circle and constant reflection coefficient circle. All right, so let's move on to the next topic. Okay, so the next topic is constant VSWR circle and constant reflection coefficient circle. So in this Smith chart, if you see these circles which are drawn with respect to the center of the Smith chart, these circles are either called constant VSWR circles or constant reflection coefficient circles. Okay, so the important point to be noted is that the center of all these circles is at the center of the Smith chart, which is this particular point. Okay, so all constant VSWR circle and all constant reflection coefficient circle have center at the center of the Smith chart. Okay, now if you see this radius and this radius and this radius, and you drop a line from this radius, you can map it to the values of the standing wave ratio. Like for example, this circle, this is a constant VSWR circle which is mapping to the value of 1.6, and also it is mapping to the value of reflection coefficient is equals to somewhat close to 0.24 maybe. Okay, so this is 0.24. This is the value of reflection coefficient, and this is the value of VSWR is equals to 1.6. Okay, so this same circle represents two different values in this Smith chart. First is its VSWR value is 1.6 and its reflection coefficient value is 0.24. Alright, now let us see this circle. If you drop a line from this radius to the bottom of the Smith chart, you can map it with the SWR and the reflection coefficient. So the VSWR in this case is somewhat close to 3.3 maybe. So VSWR is 3.3 and the corresponding reflection coefficient value is, let us say this is 0.52. So the reflection coefficient is 0.52. Alright, similarly this outermost circle, if you drop a line below, you will find that the VSWR value has a value of infinity. So VSWR is equals to infinity for this circle and the reflection coefficient is 1. Alright, so what is important to know, that a graphical representation of a VSWR circle and graphical representation of reflection coefficient circles looks something like this. These all are constant VSWR circle and constant reflection coefficient circle. All these circles have a common center point, which is the center of the Smith chart. Okay, and a single circle can represent two different parameters. The first parameter is VSWR and the second parameter is reflection coefficient. Okay, alright, so now we are good to go with the MCQs. If you have watched this lecture this far, then these MCQs are very easy for you. Now let us read the question out. The question says, the centermost point on an impedance Smith chart marked point P as indicated in the figure below represents. So here in the Smith chart, this is the center of the Smith chart, which is marked point P. There are four options given, which is locus of matched load, reflection coefficient is 0, unity voltage standing wave ratio, all of the above, none of the above. Okay, now I have chosen these questions in order to make you realize that when you know Smith chart graphically, then how fast can you solve these questions. Okay, so before giving you the complete solution, I would first like to compare between three different students. Let us say that we have student A, student B and student C. Student A have never studied Smith chart, nor does he know any concept based on transmission line. Okay, so student A knows nothing about the Smith chart, whereas student B, he have full knowledge about the transmission line theory, but the Smith chart he doesn't know much. He knows something about the Smith chart. Okay, whereas student C, he knows everything about the Smith chart, that is everything graphically about the Smith chart. Now let us try to understand the psychology of each of these students. So student A, since he have not studied transmission line theory, nor does he know about the Smith chart concepts. So he will either leave the question or he will make some incorrect choices and lose marks by negative marking. Whereas student B, he knows everything about transmission line, but he knows very little about the Smith chart basics. So what student B will do? So student B already knows that this point P is a matched load condition, and he also knows that the formula for reflection coefficient is mod of gamma is equals to ZL minus Z0 divided by ZL plus Z0. Okay, now since this is a matched load condition, the point P is a matched load point, therefore he knows that the load impedance should be equals to the characteristic impedance Z0. So when you put Z0 here in place of ZL, you get 0. That means the reflection coefficient is 0, which means second option is also correct. Okay, all right. Now next is unity voltage standing wave ratio. Now student B also knows the formula for the standing wave, voltage standing wave ratio, that is VSWR. So he knows that VSWR is equals to 1 minus reflection coefficient divided by 1 plus reflection coefficient. Sorry, the numerator is 1 plus reflection coefficient and the numerator and the denominator is 1 minus reflection coefficient. So the reflection coefficient value is found to be 0. So if you put 0 here, you will get VSWR is equals to 1. So unity voltage standing wave ratio is also a correct option. So the correct option should be D, all of the above. Alright. Okay. So student B has to solve the formula for reflection coefficient and VSWR in order to find the correct option. Now let's talk about the psychology of student C. Student C, just by looking at the Smith chart, he already knows that the point P represents matched load, plus it also represents VSWR is equals to 1, and it also represents reflection coefficient is equals to 0. Why? Because if you see this in this Smith chart, the smallest circle possible in this case is, let me choose a different color, let me choose green color. So these all are, we have studied that these all circles are constant VSWR circle. So the smallest VSWR circle will be just a point at the center. So this point is the smallest VSWR circle. Now if you draw a line here, you will see that the VSWR value is 1 here. And if you extend this line over here, you will also see that the reflection coefficient value is 0 here. So that is why option number B and option number C is also correct. So student C will not waste any time solving these formulas, and he will directly put option D as a correct option and he will move forward. Okay, so this is the power of understanding the Smith chart graphically. Alright, okay, so now let's move on to the next question. So next question says, many circles are drawn in a Smith chart used for transmission line calculations. The circles shown in the figure represent. Now the option says, the first option is unit circles, second is constant resistance circles, C is constant reactance circles, D is constant reflection coefficient circles, and last is constant VSWR circle. So are these all circles unity circles? No. We know very well that the circle which passes through the center of the Smith chart, or in other words through the locus of the matched load point, this is the locus of matched load, also it is the center of Smith chart, right? This particular circle is a unit resistance circle, which is also called unity resistance circle. Why? Because its value RL is equals to 1. Okay, so all these circles are not unity resistance circles. This circle has a value RL greater than 1, and these two circles will have a value RL less than 1. Okay, this is RL. Alright, so option A is incorrect. What about option B? Constant resistance circles. Yes, all these circles are constant resistance circles. So this particular value, this particular this circle will have some value of resistance which is constant throughout this circle. Similarly, this circle is also a constant resistance circle because throughout this circle the value of resistance is constant. So all these circles, they represent constant resistance circles. Therefore option B is correct. Constant reactance circles? No. Why? Because we know, let me choose a different color. We know that the constant reactance circles make this kind of curves. Alright, so constant reactance circle is also a incorrect option. Constant reflection coefficient circles? No, because we know that constant reflection coefficient circle and constant VSWR circle, they have a center at the center of Smith chart. So the circles should have been of this form. Let me choose blue color this time. So if a circle is drawn such that the center is the center of the Smith chart, or a bigger circle like this, all these blue color circles, they represent constant reflection coefficient circles as well as constant VSWR circle. So this option D and E is also incorrect. So the correct option is option B, which is constant resistance circle. Okay, all right. So I have one more question for you. So I am not going to solve this question for you. I am pretty much sure that after watching this lecture, you will be easily able to solve this question. Okay, so let me read this question out. The question says, match the following normalized impedances with points A, B, C, D and E on the Smith chart. So there are 4 different points given in the Smith chart, such as A, B, C, D and E. And there are 5 different points given here, which is matched load, load is short circuit, load is open circuit, purely capacitive load and purely inductive load. Okay, so you need to match these points and choose one of these options. So I hope you have understood this lecture. Please tell me your chosen option in the comment box. I will be very much happy to know that all of you have chosen the correct option for this question number 3. Alright, so I hope this lecture was helpful for you. If you have any doubts regarding the Smith chart, I will be more than happy to help you out. Thank you very much for watching this lecture.